Hey guys, it's Professor Janacek. I want to talk about a convergence test. I want to look specifically at the divergence test. Now this is a nice little test, pretty easy to work with. It doesn't have a specific look to it. Suppose we're looking at the series, the sum as k goes from 1 to infinity of just some general term, a sub k. For the divergence test, we're actually going to look at the limit as k goes to infinity of the series, of the terms of that series. If that limit is not 0, then the series diverges. Otherwise, this test is inconclusive. So you'll notice in this case, we're actually going to be looking at the limit of the terms of the series. We don't actually work with the summation. We're going to take the limit of the series. And this one only tells me if it diverges. If it doesn't diverge, then this test is actually inconclusive. So it doesn't tell me if it converges or not, just tells me divergence. So let's try some examples. Let's take the sum as k goes from 0 to infinity of 4k squared minus k cubed over 10 plus 2k cubed. Now you'll notice in this case I'm starting at 0. I need to start it at 1 though. All right, well let's just see what happens at 1. If I replace all the k values with 0, let's see what happens at 0. Replace the k's with zeros. You'll notice after that, I'm going to start this summation at 1, but everything else kind of stays the same after that. Now I do see that that first term with all the zeros, all of that is just 0, ends up going away. So this is really just the sum as k goes from 1 to infinity of 4k squared minus k cubed over 10 plus 2k cubed, right? Hope that makes sense. All right, so now for the divergence test, I don't want to look at the series. I want to take the limit as k goes to infinity of the terms of this series. Right. Well, taking the limit, let's see. I can use some of those little limit techniques we learned. This is a ratio made up of polynomials, or rational expression, if you will. We have a technique for that. I'm going to multiply by the reciprocal of the highest degree in the denominator. If I distribute that out, we're now looking at the limit as k goes to infinity of, let's see, the first term becomes 4 over k minus k cubed over k cubed, that becomes 1. In the denominator, we have 10 over k cubed plus, let's see, 2k cubed over k cubed, that just becomes 2. Now, as if we take the limit of this as k goes to infinity, as k gets really large, 4 over k goes to 0, 1 stays at just 1, 10 over k cubed also goes to 0, 2 stays just 2, so we have negative 1/2. This is definitely not 0, which means this series diverges. Again, I'm wanting this to be not equal to 0. All right, so far so good, I hope. Let's take the series as k goes from 1 to infinity of the square root of k squared plus 1 over k. All right, let's see here. Again, I'm not going to work with the series. I'm going to take the limit as k goes to infinity of the terms of this series. Notice again, I'm not putting an equal sign in there. That would be wrong. Don't do it. All right, now that I'm looking at the limit though, all right, let's play around with this. I can use an equal sign here. I'm going to go ahead and rewrite this as the limit, k goes to infinity, of, oh, check this out, square root of k squared plus 1 over k squared. We typically put things into the radical, but this time, I'm sorry, we typically take things out of the radical, but this time I'm putting it in. You'll see why, because now I can simplify this a bit, and it'll help me to take this limit. So this is the square root of k squared over k squared plus 1 over k squared. And we can all see that k squared over k squared reduces to just 1. And now I think I am ready to take that limit. The limit of 1 is just 1, but the limit as k goes to infinity of 1 over k squared, that is 0. So we end up with the square root of 1, which is just 1. This whole thing is not 0, so that tells me again that this series diverges. Okay, let's take a look at one more. Let's take the sum as k goes from 1 to infinity of k squared over 2 raised to the k. All right, so here I want to take the limit as k goes to infinity of those terms. That's k squared over 2 raised to the k. All right, let's see. If I want to take this limit, I remember good old L'Hopital helped me out here. We can use L'Hopital's rule. I'm now going to take the limit of 2k over, what's the derivative of 2 to the k? Well, that's 2 to the k times the natural log of 2. All right, well, still not sure how to take this limit, so let's use L'Hopital's rule yet again. The derivative of the numerator is just 2. The derivative of the denominator now is 2 to the k times the natural log of 2 squared. Make sure you remember how to take the derivative of 2 to the k, or 2 to the k times a constant. All right, well now looking at this, I see I only have a k there in the denominator. As k gets really large, 2 to the k also gets really large, so that whole denominator is getting really big, which means this whole thing goes to 0. Well, my original test says that the limit cannot be equal to 0, otherwise it's inconclusive. And it seems that's what we have here. This test is inconclusive. Which means I have no idea if this converges or diverges. Means we would actually have to use another test. So, divergence test, not too difficult. Simply take the limit of your terms. If that's not equal to 0, it diverges. But you'll notice the divergence test can only tell me if it diverges. It cannot tell me if the series converges. Enjoy!